Hello everyone. Let's welcome the second speaker of this session, Professor Dongling Deng. So Professor Deng now is an assistant professor at the IIS Tsinghua University. He graduated from Nankai University with 2 bachelor degrees, one in physics and one in mathematics. And then he studied at the Chen Institute, SS Chen, a very famous mathematician of Chen Institute of Mathematics, and got master degree in theoretical physics. After that, he moved to the University of Michigan and obtained his PhD degree in physics. And his thesis got the Kent Tavalinger Memorial Thesis Prize. He did his postdoc work at GQI as a postdoc fellow at the University of Maryland. And his current research interests mainly focus on quantum AI. And today, he will talk about the quantum AI recent advances. Let's welcome Professor Deng.
Okay, thank you very much, Professor Sen. First, I would like to thank all the organizers for inviting me here to give me this opportunity to give this talk here. It is my great pleasure to be here to join this wonderful conference. So today I will basically talk about quantum AI, as Professor Sen has already advertised it a little bit. So I will talk about the recent advances in this field. Since my time is quite limited, I can only scratch the surface. I hope to give you an overall picture of the whole field. Of course, due to the time limitation, I cannot cover every aspect of this field, since this field is already growing to a very large one. So I will leave all the technical details, leave out all the technical details. So if you're interested, please feel free to refer to the references, and you may also discuss with me after the talk. Okay. So okay. So then the first question is what quantum AI is, right? So we can look at this program from 2 perspectives, 2 dimensions. One is from the algorithm, the other is from the data. So if either of this is quantum, then we call it is a quantum AI program. So typically, when we talk about quantum AI, the narrow definition of quantum AI is you use quantum computer to speed up AI programs. But now this narrow definition has been extended a little bit to enclose another direction. That means you can use AI technology to solve intricate quantum many-body problems as well. So now we call all of this as quantum AI. Okay, that means if any of the data or the algorithm is quantum, then we call it quantum AI in general. So without a doubt, this field is quite interdisciplinary. It contains quantum information in the computation, machine learning, AI, in the condensed matter physics, AMO physics, etc. So this field is growing very rapidly with exciting progress made on the daily basis. Basically, every day, almost every day, we can see a paper appear on arXiv related to this field. So it is a very rapidly growing field. Okay. So today the outline of my talk is as follows. So first, I will talk about quantum enhanced machine learning AI. That means you can use quantum computer to speed up quantum AI programs. Okay, I will briefly talk about HHA algorithm, quantum generative models, and etc. I will spend a little bit more time on 2 of our recent work in my group. One is called quantum adversarial machine learning, and the other is about secure quantum distributed learning. This is basically an analog of federated learning in the classical community. Okay, Then I will move on to talk about the machine learning techniques, or more broadly, AI techniques in quantum physics. I will talk about machine learning physics of matter. I will also talk about how to use neural networks to represent quantum states efficiently, okay? So I will spend a little bit of time on talking about topological quantum compiling with reinforcement learning, basically how to use reinforcement learning techniques to find out efficient, short circuit for quantum compiling program, okay? The future challenging part, basically in this talk, since my time is quite limited, maybe I will just skip this part, okay? So the first part, quantum enhanced machine learning. So the essential idea is that since, as you already know, for many programs, quantum computer may have the potential to exhibit exponential speed up for certain computational tasks. So the idea here is that we may also use a quantum computer to speed up or innovate AI programs, okay? So I think one of the most famous algorithm is the so-called HHL algorithm. So as you may know, this target of this algorithm is basically to solve a linear equations, AX equal to B, okay? And this a matrix, a very large matrix, okay? So then from elementary algebras, you may know that basically the complexity for solving this program is if at least you need like n times log n time complexity, okay? However, if you use this HHL algorithm, then the time complexity is basically log n squared, okay? So the basic idea for this algorithm is that you can encode the like the vector B into a quantum state. Since the Hilbert space scales exponentially with the number of qubits, so then you, for n-dimensional vector B, you only need a log n number of qubits, okay? Then you can do a phase estimation algorithm to implement A inverse to this B states. Then at the end of the day, you end up with a quantum state that encode the X, okay? Then you do measurement to obtain the information encoded in this X. So in short, this algorithm has a potential exponential speed up, but as you may already notice, there may be some caveat. So the first one is that you need to transfer the classical data, like the vector B, to quantum, right? You need a so-called quantum RAM, quantum random access memory. But this one is very expensive, okay? You need exponential quantum resources to do this, okay? And also, A is well conditioned. For well conditioned matrix, there may be some other classical algorithms that also may have more efficient algorithms, okay? So at the end of the day, you only get the quantum state X, but not the X itself. You need to do maybe exponential number of measurement to obtain the X, okay? So this algorithm can be used as subroutines for many other algorithms, like Bayesian inference, quantum PCA, quantum support vector machine, etc. So more recently, as I mentioned, for this HHL algorithm, you need a quantum RAM. This is very expensive. So more recently, Professor Duan's group, they proposed a quantum generative model. So you know that for machine learning, the underlying model is usually you can reduce the you want to obtain an underlying probability distribution, right? So in most of the cases, this underlying probability distribution can be represented by using a factor graph. However, in the quantum case, there is an analog, the graph states in quantum community. So then the idea is that for a given graph, you can there corresponds to a quantum graph state. Then you can encode the variational parameters here, like in this M1, 2, M3, 4, this 2 by 2 matrix to encode the variational parameters, and then you can use a similarly like a amplitude encoding method using the the HHR algorithms, a similar algorithm, okay, to prepare a state to go from the graph state to the targeted state Q. Then you measure this Q in you do some projective measurement on this quantum state Q to obtain a probability distribution. And this probability distribution is the desired probability distribution for the underlying machine learning program. So the advantages of this model, we can look at these advantages from 3 aspects. So the first one is that this QGM model has exponential representation power. You can prove that for some of these probability distribution, you can use QGM to represent it. However, if you want to use a factor graph, you need exponentially more number of parameters. The second advantage is that there are also exponential speed ups. You can also prove that for some of the case, there exists instance such that for those instances, if you use a classical computer to do the training, you need an exponentially longer time to do the training, okay? At the end of the day, after the training, there are also exponential advantages for the inference stage, okay? So for the details, please refer to this science advanced paper listed here, okay? So more recently, we also carried out an experiment to extend the classical generative adversarial network to the quantum case, the QGAN case, okay? We carried out an experiment together with my colleagues, Professor Lu Yansun, and also Channing Zhou at the USTC. So basically, the quantum GAN is basically you just replace the generator and the discriminator in the classical GAN with the quantum devices, okay? So the motivation of doing this is that for some of the case, you can also prove that the quantum GAN may also hold the potential to exhibit exponential advantages, okay? So from our experimental result, you can see that you can indeed use quantum GAN to learn the underlying pattern from some quantum data, okay? I will not go to the details here. There are also some other approaches for using like quantum neural networks. Sometimes we call these neural networks, if you are doing a classification program, we also call this neural network as quantum classifiers. Basically, they are just variational quantum circuits, okay? Like recently, they are proposed a quantum feed-forward neural network, quantum convolutional neural network, quantum Born machine, and the quantum steady state classifiers, etc. So all these hold exponential potential to have exponential advantages over the classical counterpart. More recently, so we also introduced this so-called quantum adversarial machine learning. So I think many of you may already familiar with the classical adversarial machine learning. Okay, the well-known example is that if you intentionally perturb an image of a panda, after the perturbation, you input this image to some well-trained neural networks, then this neural network may identify this perturbed photos as a given, right? So that means you can cheat the machine learning system with a carefully designed small noise, right? There are also, you may also heard about a joke that in machine learning, you can make a pig fly, okay? I think many of you may already familiar with this joke. So this adversarial machine learning, of course, has a very important applications like in self-driving cars and in medical machine learning, etc., right? The essential idea for this adversarial machine learning is actually also very simple. So if you consider a supervised learning case, so in the supervised case, your data always has a label. So in the training process, you basically minimize some targeted loss function over some variational parameter theta, right? Then after this training, to obtain adversarial example, you just basically maximize the loss function. But here, with respect to the perturbation to the input sample to X, you add some noise, smaller delta to this sample X within some particular small region, capital delta, okay? So this basically is a optimization algorithm, optimization programs. There are also a lot of algorithms developed in the classical machine learning community to solve this algorithm, to solve this problem to obtain adversarial examples like differential evolution algorithm, fast gradient sign method, etc. So then a key question for a quantum learning is that, is this adversarial scenario also carries over to the quantum systems, right? The vulnerability of the classical neural network also carry over to quantum case or not? So the answer to this question is, of course, yes. So in this paper, we considered the quantum classifier. We also add a little bit of noise to the quantum data, like this panda encoded in quantum states. Then we use a variational quantum circuit to do the classification. And we show that after you add a little bit of noise to this photo, then the quantum classifier will identify as a given. So we considered different scenarios like a targeted attack and untargeted attack, etc. Okay. So here we show a little bit concrete examples. We tested this algorithm like in the MList case. So for this untargeted attack here, like you may add a little bit noise like this adversarial example, like to the original clean samples. Then this quantum classifier will identify, for instance, for this digital 1, will identify it as a digital 9 with a very high probability confidence level, okay? So we also consider this untargeted attack case, okay? So so another question you may wonder is that, is there like a universal adversarial example or universal adversarial perturbation that can cheat a set of quantum classifiers, right? So you use a single adversarial sample to cheat a set of classifiers, or you add a single perturbation, adversarial perturbation. Existing theorems. So the first theorem is that basically you do not need to look at these details of the theorem. So basically you only need to look at this inequality here. So basically the conclusion is that you only need to increase the perturbation for a set of K classifiers. You only need to increase the strength of the perturbation by log K, okay? Then you can ensure that the universal adversarial risk is already bounded by some constant risk R0, okay? The basic idea of this proof is you just use the concentration of measurement phenomena, and you also use the De Morgan's law. So essentially, this is basically from the geometric picture of concentration of measure. That means in a very hierarchical space, usually most of the measurement values will concentrate to some small region. Okay. For the adversarial perturbation case, we also prove that you can indeed, for like n samples, row 1 through row n, you can also add a little bit of noise to these samples, identify noise to make all of them to be adversarial examples, okay? And you can bound all these adversarial risks, okay? So the proof of the theorems, the basic idea here is you need to use the quantum no-free-lunch theorem, which is a quantum analog of the classical no-free-lunch theorem. Okay. So the take-home message is that although quantum classifier may have a potential exponential advantages over classical classifiers, the vulnerability program issues are still there. So you should this vulnerability of quantum learning basically demands extra care. More recently, we actually wrote a review paper for these vulnerability programs in quantum AI. This review paper is writing in Chinese, is published in the 物理学报 in Chinese. Okay. So now I talked about you can speed up machine learning tasks with quantum computer. Another advantage for quantum information is that you may, from the security perspective, right? So actually, you can also explore the security advantages for quantum machine learning. Okay, so that is the quantum federated learning. Okay, so so consider a scenario that several clients want to train a shared model with their private data, but they don't want their data to be revealed to other parties, right? So in the classical case, there is a federated approach to this. However, at there, the security is you need to make some assumption for the security proof. But for the quantum case, you can use the blind quantum computing to achieve this. This has the advantage that the security is basically unconditional. Okay. And also, this approach can apply to both quantum data and classical data. Okay. So the essential idea is to use the blind quantum computing scheme. Okay. So for details, I do not have time to go through the details. Okay. So here's however the difference a little bit subtlety here is that you may take care of the gradient attack because the model is publicly shared, right? If you share the gradient, then there may be algorithm gradient attack you need to consider. So then, in order to avoid this gradient attack, to defend the gradient attack, we should add some random noise to this gradient. This is the idea of the differential privacy. Okay. So okay. So as the numerical simulation shows here, so with differential privacy, basically your private data is not revealed to anyone. The computation is basically unconditional secure. Okay. So I just talked about one direction for the quantum AI. That means you can use quantum computer to speed up or innovate machine learning programs. Okay. Another direction is that you may also use techniques and tools from the AI community to solve quantum problems. The direct application is the machine learning phases of matter. So in machine learning, basically for the supervisor case, right? You can identify a photo as a cat or a dog. So if you replace this photo of cat and a dog with some experimentally observed photos, for instance, from the STM image, right? Then you can identify different phases of matter. Okay, this is the machine learning idea of machine learning phases of matter. You can also use this approach to identify the phase transition point and study the scaling property of this phase transition. There's already a lot of work along this direction. For instance, I just list some of these papers here. You may also use unsupervised learning to do this phase identification. Okay. Now there's already a lot of paper along this line also. Okay, so as I just mentioned that the vulnerabilities program for quantum classifiers, right? There's a vulnerability program. So if you use the machine learning techniques to identify different phases of matter, so there's also vulnerability programs. You also need to take care about this. Okay, so this is the essential idea. So if, for instance, if you consider an image from a time of flight, this is a typical image obtained from the laboratory in the cold atom experiment. So if you add a little bit of noise to this time of flight image, you put this image to the artificial neural network, then it will give you some wrong prediction. Okay. So we also did some numerical simulations on this. For instance, we considered the 2D icing model. So here I want to emphasize, like in this case, like even you just change a single pixel of the spin configuration of the icing model, it will enable to cheat the neural network. Okay, at a very high level of confidence. Okay, so that means we should, when we use this technique, we should really pay attention to the vulnerability aspect. So there are also some works of using neural networks to represent quantum many-body states. Okay, so I don't have time to cover this part. So more recently, actually, this approach have been extended to the solving the open quantum systems. Okay, the key idea here is that you can use this representation are very efficient. That means you can use like polynomial number of parameters to describe a subspace of the total Hilbert space of the n-qubit systems. Okay, so there are other applications of this neural network states, like detecting quantum non-locality, quantum tomography, reconstructing quantum density state in the computing the auto time ordered correlator, etc. So here I just only list partial of these works. There are many more. Okay. So I will spend my time is always almost up. Okay. So as the last 2 minutes, I will talk about the quantum comparing with reinforcement learning. So the key idea is that, so if we consider a quantum comparing program, so quantum comparing means you want to decompose a targeted unitary into a sequence of elementary unitaries, right? So this program is very similar to the program of solving the scrambled cube. Okay, so here I plot one-to-one correspondence, plot a table for the one-to-one correspondence of these two programs for solving the Rubik cube, right? So the initial state of the comparing program is a unitary to be approximated. This corresponds to the scrambled cube. And the target state is just the identity matrix. And the target for the cube is the solved cube, right? The basic moves is basically a gate from the universal set. And here it corresponds to the rotation of one phase. So the good thing is that we tested this. You can use a reinforcement learning approach to solve this scrambled cube, right? Then you can directly apply this reinforcement learning algorithm to solve this quantum comparing problem. So we tested this in breeding Fibonacci onions. Here's the performance of the benchmark. The good thing is that I want to emphasize here that, as you can see from here, that if you use reinforcement learning, the circuit you find is much shorter than the typical circuit you find with some traditional algorithm like Solovay-Kitaev algorithm, etc. Okay, so this is a really a good advantage, especially for the NISQ area. Okay, so I think my time is up. So I will end up here. Okay, thank you for your attention. Okay.
Thanks, Dongling, for the very nice talk. I think maybe one quick question. Any questions? Okay, let me ask a question. Dongling, you mentioned that the quantum can help with the representation and also the inference. So do you think, or are there any works that quantum can speed up the training?
You mean like
yeah, in the machine learning, the training, how to is there any result can help to speed up the training?
Yes. Indeed. Actually, there's a rigorous proof by Liu Yunchao. So recently they published a paper for a supervised learning. They indeed and a proof that it indeed has a exponential speed up with rigorous proof. The key idea is that you can use the implement this discretized logarithmic algorithms. You map the data. You first map the data to some feature space, and this map is based on some quantum Fourier transformation, basically. And this quantum Fourier transformation gives you the exponential speed up.
Oh, okay.
Under some reasonable assumptions. Yeah, that's the essential.
I see. Thank you. Thank you very much for the nice talk.
Thank you very much. Thank you.